Welcome back to Essentials of Computer Architecture and Organizations. We're looking forward to, as we're moving along in our class, to get into more of the involved topics. And so we have just finished with the first three chapters, the basics, the building blocks that we need to start to do computational architectures. Um, and so now we will start the first, what I would say is the main section of material is getting into the processor. And today with chapter 4, we're going to be talking about the variety of processors and computational engines. So let's begin with some thoughts on terminology. The term processor and computational engine refer broadly to any mechanism that drives computation. There's a wide variety of sizes and complexity, and processors is a key element in all computational systems. Interesting little bit of tidbit. If you've ever seen the movie Hidden Figures, it was about what was called the computers that NASA used with the beginning of the space program leading up to Apollo landing on the moon. And a computer, typically, as we think of today, we think of it as a hardware. You're probably viewing this lecture from a computer. But back then, it was actually a person, and a computer was someone that would compute because they didn't have the resources that we have now with processors, the computational capabilities, and that was just at its infancy. And they actually introduced the first idea of using a mainframe for something like that from IBM. So why don't we talk a little bit about architecture? We will introduce two different types of architecture. One is called the von Neumann architecture, and then we'll mention the Harvard architecture that has a slight difference in terms of how it wants to describe the memory. So this architecture, the von Neumann, it's a characteristic of most modern processors. It is in reference to John von Neumann, and here's a picture of him down in the corner, who was a pioneer in computer architecture. And the Harvard architecture has two different types of memory, but in the von Neumann architecture just has one. It aggregates it all together. So the fundamental concept is a stored program that is a program that is in the same memory as the data. And so the three basic components that interact to form a computational system is the processor, the memory, and the I/O facilities, the input and output facilities. And so for this section, we're going to be focusing on the processor. So here is an illustration of the von Neumann architecture. It has these three elements, and these three elements work together, communicate with one another. You have the processor where all of the computational elements are done and information is fed into it about what to be doing. There's the memory that it needs to be doing those computations, and then it's storing things back into other types of memory. And you have this input, output facilities, this backplane where all of that is connected. And you can have various other types of devices. We're used to thinking in terms of having a mouse, having a keyboard, but there's Bluetooth, there's other specialty types of devices that can also be included. So the processor, it's a digital device. And remember, we just finished talking about digital logic. And so with all of the things that we've thought about up to this point, this is what's in the processor. It performs computation involving multiple steps. It has a wide variety of capability, and it has the mechanisms to handle a variety of things, fixed logic, selectable logic, parameterized logic, and programmable logic. And so it is a flexible device that, based on what you tell it to do, what is it, are the control lines that configure it in a certain way, step by step, it can be doing these various types of logical operations. So there's a hierarchical structure, and when we're thinking about processors, most computer architecture follow a hierarchical approach. The subparts of a large central processor are sophisticated enough to meet our definition of a processor. Some engineers use the term computational engine for a subpiece that is less powerful than the main processor. And we'll start to see some ways how that unfolds. I'd like to be thinking about an arithmetic logic unit, which is one of the main things that you have in a processor, and that'll come up shortly. So here's a way of looking at the processor hierarchy and the various things that are brought together. I mentioned the arithmetic logic unit. And so we can have an arithmetic engine. You can have various queries. How do you handle that things, there's an interrupt that it says, here's something that comes in that I need to actually act upon. There can be a graphic engine, whether that be a graphic card that's dealing with a GUI, graphical user interface. You can have coprocessors that are dealing with things like trigonometry, and other kind of components. And so the sky's the limit as you move forward. So the main components of a conventional processor, there's a controller to coordinate operations, and often this is omitted from the architectural diagrams. And when we get later in some of the material in the course, we will see how some of that starts to work its way into things that we have to consider. There's arithmetic logic unit, where you can be doing all kinds of different things, saying you need to do an addition, a subtraction, a multiplication, a division. You need to be doing a load from memory, store to memory. There's logical operations. You want to be doing it and, or, etc. There's local data storage, where you read and write. You have things that have the program, the instructions that you're using. There's the internal connections within the processor, and there's also external interfaces that deal with the bus. So in terms of a conventional processor, here's another way of looking at it. You have the arithmetic logic unit, you have the controller, the local storage, the internal interconnections that helps it to function internally among these basic elements. And then you have the interface where it connects with the external world with other types of things that are part of the reason why you're using that processor. So let's take each of those main areas one at a time and talk about them in a little bit more detail. So first of all, the controller, has the overall responsibility for execution. It moves through sequences of steps. So you start with step 1 in your program, you move to step 2, on to step 3, and so it sequences through the instructions. It coordinates other units. There's times when it needs to be reading memory, writing to memory, have a couple of operands that are needed to do a specific step that it has to walk through as it goes sequentially through each of the instructions. Timing-based operation, it knows how long each unit requires and schedules steps accordingly. So it's like the conductor of a symphony, if you will, or the coach of a team, that it's keeping everybody in a line and making sure that they're going by agreed upon rules and how you execute things in a smooth fashion. The next main component is the arithmetic logic unit, and it operates as directed by the controller. So it has control functions that you select which one of those control functions that you want to do. So it can do arithmetic operations, it can do Boolean operations, and it can perform one operation at a time as directed. So one operation could be an arithmetic, and the next one can be a Boolean, the next one can be a load, the next one can be a store, and it just goes on and on and on. In terms of the internal interconnections, it allows transfer of values among units of the processor, which sometimes this is called data paths. And instead of going to external memory, we're talking about just things to do internal on that single chip that's in that processor. Finally, there's the external interfaces that can handle communications between the processors and the rest of the computer system. And it provides interactions with external memory as well as external I/O devices. So, and then we have the local storage, the local data storage. This is where the data values for operations are held. The values must be inserted, and that is loaded from memory before the operation can be performed. And typically, it's implemented with registers. And so we will be talking about this more, and we'll have an example when we start to get into assembly language programming with the emulator, that we'll start to get some specific experience of what it's like to be dealing with those registers. The arithmetic logic unit, it's the main computational engine and conventional processor. And we will get a chance to look at that closer, to look at some of the early on examples of how that has been developed and used. You can actually make an arithmetic logic unit directly out of digital logic. And so we'll show some examples of how that works. It's a complex unit that can perform a variety of tasks. And so it's amazing without having to change any wires, switch things. It's all there just by commanding it to do things. It can do arithmetic, it can do shifts, it can do Boolean. All of these types of operations are the things that can take place. And in the if we're doing programming, as we'll be doing with the emulator, we will show that there's distinct commands that are used for each one of these functions. And so not as high level in terms of the programming, but in assembly language, we do have a way of doing all these functions, and it's interesting to get a chance to program at that level. What type of categories and roles are there in terms of processors? You can have coprocessors where it has a more dedicated function. A GPU, a graphic processing unit, is an example, and sometimes those can be used to have a computational engine that can make things run faster. You can have microcontrollers. When we start to play with our Arduino unit, that's an example of a microcontroller, which is a programmable, dedicated set of functions that isn't as so sophisticated as a full-fledged processor, but it has some of those features of programmability. There's embedded system processors, and there's general purpose processors. And so those are just some categories here. We'll walk through them a little bit as we go along. So for coprocessors, they operate in conjunction with and under the control of another processor. So usually they have a special purpose, performing a single task, and it operates at high speed. So if you wanted to have a 4K graphical user interface, it would make sense to have a GPU as an example of a coprocessor to do those types of processing. Or if you're having some heavy computing, instead of just using it for your graphical interface, you can have a dedicated processor that is attempting to accelerate floating point mathematical computations. And so that would be another thing that would be useful. A microcontroller, it's a programmable device. It's dedicated control of a physical system. We will show some examples of how that will play out with our Arduino. Examples can be that you can control some aspect of an automobile engine. You don't need a full computer to do something to continually monitor some function in an engine or a grocery store door. And so something that's more in line with that would be this kind of a processor or microcontroller. So the negative, it's extremely limited. It's a slow processor and has a small amount of memory, but it has very low power consumption. So you could easily just run it on a battery and it's going to run and run and run. So here is some pseudocode that's walking you through what a microcontroller performing an automatic door opening function would look like. And so it's constantly waiting forever for the sensor to be tripped. And once it is tripped, the power to the door monitor, it's turned on. It turns on the power to the door monitor. It waits for a signal that indicates that the door is to open. So you ever seen like an automatic door open? The first thing you get close to it, it gets to a point where, okay, now I need to watch something's going to happen, and then you step on the sensor, and as soon as that sensor is tripped, the door is open. So that pad, that sensory pad that's leading up to the door, or the sensor that detects that you're within 3 feet of the door, it then opens it. Then it waits for the sensor to reset, and then there's a delay, say, of 10 seconds, and it turns off power to the door motor and the door closes. So that's an example of where a microcontroller would excel. An embedded system processor, it runs sophisticated electronic devices, may be more power than a microcontroller. It generally is aimed to try and have low power consumption. So an example would be to control a DVD player or Blu-ray player, which would include the commands to receive that would come from a remote control. So having some Bluetooth type of capability, as well as being able to deal with inputs from the front panel. So this would be something that would be embedded into a device that has a certain level of function, but say it would be more powerful, more elaborate than just opening and closing a door. General purpose computer, this is like something that you would have in your laptop or desktop. So it's a more powerful type of processor. It's completely programmable. It has all functionality that you would need to do for a variety of tasks. And the power consumption is a secondary factor. So having it plugged into the wall or having a little bit larger battery is typically the case of what you would see. And so a CPU is an example. A CPU in a personal computer, as I said, is a good example of that. So how were processors implemented? Originally, they were done in discrete logic. As they developed, they were put into single circuit boards, eventually going into a single chip. And now, usually they're part of a single chip that you can have a system on a chip and other things like that. The discrete logic in the very beginning, it wasn't even just using transistors. They were using tubes, vacuum tubes, and then there was a big transition and move going to transistors, which led to the digital logic in a more reliable fashion. So that's just another aside to be thinking about. So what is a programmable device? To a software engineer, programming means writing, compiling, and loading code into memory. It's executing the resulting memory image. So that's what it means for software. For hardware, a programmable device has a processor separate from the program it runs, and may have the program burned onto a chip. So this is a little bit more dedicated, and speed, low power, high reliability would be the kind of things that you would be hearing in terms of hardware processing. So what is the fetch execute cycle for basic? This is something that's for the basis for programmable processors. It allows the processor to move through program steps automatically. And it's implemented by processor hardware. At some level, every programming processor implements a fetch execute cycle. So you get a command, you execute a command. You get a command, you execute a command. And so we will be talking about pipeline architectures, and so we'll see more about that as we go. So here's an example of this. You get a command, you execute. So first thing is you fetch, go to the next step in the program, you perform that step, and then you go back. And you repeat forever until you get an end of program termination notice. And this will be something we'll talk about in more detail as we go. So program translations. Programs require a program to be in memory, and it has to be represented in binary, the language, the basis in which digital programming is done. Programmers refer to a program as a readable by humans, which is a high-level language. So that's how we think. But we need to translate this into the terms of what a computer thinks and operates, which is at this low level, the way that a processor sees it. And that's in binary. So the solution is allow programmers to write code in a readably high-level language and translate it to binary. So you have a compiler. And so we use computer software to perform this translation, sorry. And here's an example of what an illustration of program transition would look like. So you have the source code. So this is like whatever language that you're going to be considering, whether it be C or C++, or it could be assembly language when we're getting a little bit lower. You have the preprocessor to see if there's any errors, anything that might be missing to make this not work properly. So it's a little bit more conditioned. We'll see a little bit of an example of that when we look at the assembly language, that sometimes what is at the highest level needs to be spelled out in a little bit more detail with more steps. And then having the compiler, we then have the assembly code, and then we pass it on to the assembler, which links things together. So there's other types of libraries that need to be used, and so there's references that you don't have to program every time, and so having a nice, healthy library is going to make things much easier. So once you put that all together, then you have your binary object code, and that's what's actually is executed. So you have the clock rate and the instruction rate, which aren't necessarily the same thing. A lot of times we use a clock rate to give us some basis to compare how well a computer is doing. And so it is a rate in which the gates are clocked, provides a measure of the underlying hardware speed. The instruction rate, instead, it measures the number of instructions a processor can execute per unit time. And so sometimes you'll hear about the clock rate, sometimes you'll hear about how many instructions per second that a processor can perform. Some processors, a given instruction may take more clock cycles than other instructions. So that's one of the reasons why the instruction rate and the clock rate are not exactly the same. So as an example, multiplication can take longer than addition. So it would take more cycles, more instructions to get things through. You need to have the ability to stop a processor's. So if you have a processor that runs fetch execute indefinitely, how are you going to get it to stop and not remain in an infinite loop? The software must plan the next step. Two possibilities exist when that last step of computation finishes. The smallest embedded systems, for that case, the code enters a loop testing for a change in input. The input changes and it's going to change what it does. For a larger system, operating system, the operating system runs and executes on an infinite loop, and there needs to be some kind of control to tell it when it's completed. So to reduce power consumption, hardware may provide a way to put the processor in sleep until there is I/O activity occurring. And so that'll be something in the latter part of the course that we'll get to. So we talked about stopping the processor, now starting. Processor hardware includes a reset line that stops the fetch execute cycle. For power down, reset is used, the line is asserted. During power up, logic holds the reset until the processor and memory are initialized. Power up steps is also known as bootstrapped. And I talked about the BIOS a couple chapters ago. We gave an example of a simple BIOS-like function of what that would mean, getting things ready for it to actually do the computation. So let's summarize what we've talked about. Processors perform a computation involving multiple steps. That's where the real elegance comes in. Using the same hardware, it can adapt and do one thing at a time in an orchestrated, orderly fashion. There's many types of processors, coprocessors that have a dedicated function, a microcontroller that can be used, say, for opening a door or something like that. Embedded system processors that can be used, say, in a Blu-ray player, a DVD player, something like that. And a general purpose processor that you would have in a common personal computer or a laptop. The arithmetic logic unit, or ALU, it performs the basic arithmetic and Boolean operations. This is all can be implemented in basic digital logic, and we will give some examples of how that looks later in the course. Hardware in programmable processor runs fetch, execute, cycle. It runs in this loop, fetch, execute, fetch, execute, fetch, execute. It keeps doing that. This happens until a processor is powered down. And so there's some type of interrupt, which we'll get into when we talk about input and output, that tells it it is now time to finish that process. Well, thank you very much. That ends our lecture, and we will keep going in our journey as we work through this material. Thank you.